All right, so we got a new week. We're starting in on a new chapter here, chapter 4, and we're going to introduce a new functional group talking about cyclic alkanes. Okay, so just to review, last week we discussed alkanes. All right, so for example, hexane. And we said what made an alkane is that there are only going to be carbons and hydrogens. And what was the other criteria? All single bonds. Absolutely, yep. Only carbons and hydrogens and single bonds. Okay, so when we talk about cyclic alkanes, an example would be this hexagon here, cyclohexane. All right, and so what makes a cyclic alkane? Again, only carbons and hydrogens, only single bonds, but now we have a ring. So if you see a ring in that structure, it's classified as a cyclic alkane. All right? So thinking about properties of this functional group here, what do we think? Are these cyclic alkanes going to be polar or nonpolar? Nonpolar, right? Still only carbons and hydrogens. So we don't have any polar group in there, so these are still very nonpolar molecules. All right, and much like alkanes, they're kind of boring. They have no reactions that are associated with this functional group, except that one important exception, combustion reactions. All right, so like alkanes, cyclic alkanes are kind of boring. They're just nonpolar molecules. There's not much cool chemistry that happens, other than you can blow them apart by heating them up with some oxygen. Okay. Let's sort of take a step back and remind ourselves. We talked about boiling point last class, or with regard to our last functional group. All right, so I want you to take these molecules here and arrange them in terms of increasing boiling point. Let's call these A, B, and C here. So which one's going to have the lowest boiling point? A. Which one's going to have the highest boiling point? B. And C's in the middle. And so how do we make that determination? The chain length, right? Okay, but let's think here. Remember that these nonpolar molecules, the only forces that they have between neighboring molecules are those dispersion forces. So why are dispersion forces greater for bigger molecules? Because this is a force that is proportional to the surface area of those molecules, right? So the longer it is, there's just more surface going on that can interact with its neighbors. All right, so it is based on chain length, but again, the real logic there is it ties to the surface area. Okay, so now let's look at, for example, hexane versus cyclohexane. Okay, hexane has a boiling point around 69 degrees Celsius. whereas cyclohexane has a boiling point around 80 degrees Celsius. All right, so fairly similar. No, we're not talking about like a 100-degree difference or something like that. But we can see that our cyclic alkane has a higher boiling point than the straight chain. All right, and so why is that? Again, going back to that surface area argument, by tying these two ends together, you've created this big surface on your cyclic molecule. So you've just given it more surface area and thus stronger dispersion forces. So we can say cyclic alkanes have higher boiling points than straight chain alkanes with the same number of carbons. All right, and why is that? More surface area. Okay, so then again, I'm going to ask you to rank these in terms of increasing boiling point. Nope. All right, so which one's going to have the lowest boiling point? A, right, it's the smallest and it's an alkane. B and C both have 5 carbons, okay, but which one of the two is going to have the lower boiling point, B or C? C, right? The straight chain will have a lower boiling point than the cyclic molecule. Cool. All right, so we're going to learn some terminology here. We actually sort of discussed this very briefly at some point. We're going to more formally introduce this concept of constitutional isomers. All right, a constitutional isomer has the same molecular formula but a different connectivity of atoms. All right, by that I just simply mean they have different structures. Okay, so an example, if we go back to hexane, everybody take a second and give me the molecular formula for hexane. C what? H what? How many carbons? How many hydrogens? 14. So hexane, 6 carbons and 14 hydrogens, all arranged in a straight line, right? If I take these same number of carbons, but I rearrange them to create something like this, okay, this also has the formula C6H14. All right, everybody take a second and name this molecule for me. We said this one was hexane. What's the other one? Anybody got it? 3-methyl pentane. All right, so we got two distinct molecules. We name them completely different, right? But they share that same molecular formula. They share the same number of carbons and the same number of hydrogens. So this would be a pair of constitutional isomers. Okay? In fact, all alkanes, both straight and branched, always have this sort of formula to their molecular formulas where however many carbons you have, so we're going to say we have n carbons in this straight chain, or in this chain, the number of hydrogens is 2 times that number plus an additional 2. And you can convince yourself that works with both of these here, right? I have 6 carbons, 6 times 2 is 12, add another 2, that gets me to 14. Okay, so all alkanes, whether they're branched, cyclic, whatever, no, I lied, I'm sorry. Whether they're straight or branched will have this same formula here. Okay, cyclic alkanes do not follow this same sort of formula here. So everybody take a second, let's look at cyclohexane, these 6 carbons in a hexagon. Okay, take a second and tell me what my formula, my molecular formula is for this molecule. I got 6 carbons. How many hydrogens? Right, so each one of these, 2, 4, 6, 8, 10, 12. It's absolutely C6H12. And so these are right? Cyclohexane and hexane are not constitutional isomers. They do not have the same molecular formula. Okay? What does is very similar, another 6 carbons. But if I put a double bond in there, this will also have that same C6H12 formula. And what do we call this functional group here that's in this molecule on the right? An alkene. So cyclic alkanes and alkenes, they are constitutional isomers. They have this formula Cn, and H is just 2N. All right, so we have this new term, constitutional isomers. These are different molecules, all right? They got different properties, different boiling points, all that jazz, okay? But they do share the same molecular formula, which is why they get this special name, constitutional isomers. So I'm going to put down an alkene, rather. All right, so here's an alkene. You're going to draw me a cyclic alkane that is its constitutional isomer. right, so my formula for this alkene would be C4H8. All right, so I need to draw a 4-carbon ring. How do we draw that? What does it look like? It's a square. Yeah. Boom. So there is a cyclic alkane that is a constitutional isomer for this alkene. There actually would have been one more that you could have given me, and that would be a triangle with a methyl group sticking off of it. That also is a cyclic alkane. You got a ring in there. It's got those 4 carbons. If you counted up the hydrogens, you can also see that it fits that same formula, C4H8. All right, so these boxes, these triangles, they may look a little less familiar than the hexagons that we've been looking at, and that is because they are far more rare. They are not even close to as stable. It is not very stable to arrange these 3 carbons into this whole triangle here. All right, so that's what we're going to talk about next, is this idea of ring stability and the different factors that will affect how stable a particular ring is. So step 1, let's understand what this graph is saying here, okay? If we take a compound, so for example, our box, right, C4H8, we react it with oxygen in a combustion reaction. What are the 2 products of a combustion reaction? Carbon dioxide and water. Okay, this is a combustion reaction. Take some fuel, react it with oxygen, you get CO2 and H2O. All right, I'm going to sort of state this formula for my box here. Every single one of these corners is a CH2, 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 CH2. All right, so I can sort of organize my formula here. CH2, there's 4 of them. All right, and for every one of those carbons that react, it's going to produce CO2. So if I balance that, I would put a 4. And every one of those H2s that react is going to produce water. So that would also give me 4. Okay, I guess I can be good about my balancing here. What's this, 6? So in general, for a ring, we can give it this sort of combustion reaction where we put CH2 to the N, so this is going to be the size of my ring. Plus oxygen, I would get N molecules of CO2 and N molecules of H2O. All right, and again with these combustion reactions, why we as humans have loved them and used them to power the world is because they also release a lot of energy. Right? When you break up this ring into carbon dioxide and water, that's accompanied by a big release of energy. Okay? All right, now because this reaction will just produce more water and more carbon dioxide for bigger rings, you'll always get more energy released for larger rings, right? You just get more energy that's released because you're creating more products, more molecules of carbon dioxide, more molecules of water, okay? So just measuring the amount of energy that's released isn't really going to tell you very much because, again, it's just always going to increase depending on how big your ring is, all right? So instead, what we are going to look is the energy released per unit of CH2. All right, so they do these combustion reactions with each ring. They measure how much energy is produced, and then they divide it by the number of carbons. So we can get this sort of relative amount. We can take out the fact that it's always going to be greater depending on how big the ring is. All right, and why is this interesting? Let's go back to our Chem 1B in these free energy diagrams here. Okay, remember on one side are our reactant energy, on the other side is our product energy. These are reactions that release a bunch of energy, right? So that means that my products are going to be sitting at a lower energy level than my reactants, right? My products are, again, that carbon dioxide and water. My reactant is my cyclic alkane. Got these little curves here. Okay. Again, what we're really going to look at is the energy per our number of CH2s. That's what we're interested in. Okay? So let's say that this alkane that I just drew, this curve for, this is a very stable cyclic alkane. Nice and stable. All right? If I were to look at an unstable cyclic alkane, where would we expect the energy of our reactants to start off as? Higher or lower than our stable cyclic alkane? If you're unstable, right? Do we like low energy or high energy? No, we like low energy. Low energy is nice and stable. High energy means bad. Okay? Low energy is when something's very, very stable. So a less stable ring means that I'm going to start out somewhere up here. Okay, so here's my unstable cyclic alkane. Okay? But importantly, because in this reaction I'm always producing the same products, my product energy level is going to be the same. Right? So the bottom line is if I start out with an alkane that's nice and stable, I'm going to release a small amount of energy. Whereas if I start out with an alkane that's unstable, so it's sitting up here at a higher energy level, it's going to release more energy, right? So I'm going to get a large amount of energy released.
Why does the energy go up before it goes down?
The hump?
Yeah.
So there's something called the activation energy. The bottom line is like whenever you start to make or break bonds, that process of a bond breaking is going to increase the energy. So there's always this little hump that a reaction has to get over.
Okay.
The size of that hump depends on the kinetics, how quick the reaction is. Okay, so if we look at this energy per unit of CH2, we can get an idea about how stable or unstable a ring is. So again, they did this experiment. They repeated it for rings, 1 of 3 carbons, 1 of 4 carbons, 1 of 5 carbons, 6 carbons, etc., etc. They did these combustion reactions. They measured how much energy was produced, and then they divided it by the number of carbons, and that's this plot that you see here. Okay? So this gives us an idea of what's our most stable rings and what are our least stable rings. All right? What's the most stable number of carbons that you can have in a ring? 6 and 14. 14, who knew, right? That's a random one. 6 we see quite a lot though. Okay? So why are 6-membered rings so much more common? They are just more stable. Okay? And what's the least stable type of ring that we see? Those triangles, right? Those 3 carbons in our ring, that's minimally stable, as unstable as you can get. All right, so why is that? There are 2 big factors that affect ring stability. Okay. The first one is what's called angle strain. All right, if we look at one of our rings here, what's the hybridization on this carbon here? It's got these 2 hydrogens sticking off of it. So what's the hybridization of that carbon? sp3. And sp3 hybridized carbons want to have a very specific bond angle. So sp3 hybridized carbons want a bond angle of 109.5 degrees. Anything else, if it has to adopt any other bond angle, that's just going to raise the energy of that molecule. So this angle strain is increased energy anytime a molecule has to adopt a non-ideal bond angle. All right, if we look at a triangle here, all right, this is an equilateral triangle. So what is each one of these bond angles going to be? Does anybody remember from geometry? The whole thing's going to be 360. So divide that by 3. This would be a 60-degree bond angle. So when you create a 3-membered ring, you are forcing those carbons to adopt a bond angle of only 60 degrees, which makes them super duper mad, right? They want to be at a bond angle of 109.5. So part of the reason why this bar is so high on this graph is because those bonds are much smaller than ideal, and that raises the energy of that molecule. Okay. The other big factor is what's called torsional strain. All right, and this is something that we talked a bit about last time. We didn't call it torsional strain, but we looked at all these different Newman projections and calculated their energy, and we found that when bonds were eclipsed, they had a much higher energy than when they were staggered, right? That's what we call torsional strain. So an increase in energy due to eclipsed bonds. All right, so we're going to take a look at a few cyclic alkanes. In particular, here are the smaller ones, and look at them for angle strain and torsional strain. If we start with our cyclopropane, the 3-membered ring here, we already discussed about how it has a bunch of angle strain because of that 60-degree bond angle, right? So it's far from that ideal 109.5, okay? There are 2 sort of representations of molecules here. The one on the right might be a little bit more familiar looking because that's what our model kits look like. This is what's called a ball and stick representation, okay? But we don't want to be too faked out by this picture of a molecule here because these are all just like kind of BS illustrations of what molecules look like. If you hopped into your magic school bus and you shrunk on down and looked at this molecule, it wouldn't look like a bunch of balls and sticks, right? That's not what molecules actually look like. We have this representation. It's a great one in terms of illustrating geometry and where bonds are and this staggered versus eclipse business, but it's still not like 100% accurate, right? And in fact, the electrons in bonds and the electrons around atoms, they take up quite a bit of space. And so the picture that you see on the left is what's called a space-filling model. It kind of more accurately represents how much room electrons take up in a molecule. It's also a lot harder to look at and see what's going on exactly, right? So there are two different representations here. They kind of make two different points, all right? So anyways, you will see both of these quite frequently. If we were to sort of just do our regular old structure here, what you would see is that in this triangle, just because it has to adopt this sort of planar configuration, not only do you have that crap 60-degree bond angle, but every single one of those bonds are also eclipsed compared to their neighbors, right? So they're all parallel to one another around that ring. So this triangle, this three-membered ring, is the worst of both worlds, which is why it is so high energy. Not only does it have a boatload of angle strain, but it also has 100% maximal torsion strain. All those bonds are eclipsed. All right, so our triangle here has a lot of both angle and torsional strain. Okay, let's take a look at the four-membered ring, the box. What's the bond angle in my box? All right, so this is going to be approximately 90 degrees. Okay, that would be if it was completely flat. Because there are four atoms, now the molecule can kind of kink itself a little bit to try to increase those bond angles. So it gets a little bit bigger than 90, but not much. So we still have a good bit of angle strain here. Okay. We're going to do a Newman projection of this molecule. So here's my molecule. I'm going to look down this particular bond. And we can see that because it's sort of adopted this little kink, our bonds are not quite eclipsed, but they're still pretty bad. They're still pretty close to being eclipsed. So again, we do a little bit better. We can say that we still have both the angle and torsional strain. All right, we did a little bit better. We got a little bit bigger bonds. We got our bonds to be not perfectly eclipsed, a little bit off, but we still have quite a bit of both, which is why if we look at the energy of our square compared to our triangle, right? Yeah, we go down a little bit, but it's not that great. Okay. Now we're going to go to five-membered ring, and all of a sudden, boom, that thing just like plummets in energy, right? We get a huge decrease in energy from 4 carbons to 5 carbons, okay? So let's think about why that is. So first of all, somebody Google for me, what is the angle in what's called a regular pentagon? I don't know what it is off the top of my head. Somebody Google it.
Interior or the exterior?
Interior.
108.
108, okay? So now all of a sudden when we have a pentagon, I don't know where my hidden drawing is, okay. That was pretty terrible, but whatever. All right, now we're pretty freaking close to our ideal here, right? So one of the reasons we have such a massive drop in energy is because now our bonds are much, much closer to that ideal energy, that ideal angle of 109.5, okay? But if it was completely flat, you would have all these eclipsed bonds, right? And again, that's an added bit of energy. So again, the molecule can kind of fudge it a little bit. It'll kink itself a little bit so that it's not completely flat. If we look at a Newman projection of what that would look like, all right, we can see that we are pretty close to staggered. Not 100% of the way there, right? But they're not perfectly staggered, but we are pretty close. So we've improved dramatically on our angle strain because we can adopt this near ideal 109, right? 108 is pretty close, okay? As well as it can sort of kink itself so that these bonds are pretty close to being staggered, which again is why we see such a dramatic decrease in energy. All right, and then lastly, if we look at a 6-membered ring here, this is the most stable that we can get on the smaller end. Okay, now there's enough carbons that this thing has a lot of wiggle room to kind of kink itself into an ideal bond angle. All right, it forms what's called a chair structure, and we're going to spend an entire class next time learning how to draw and interpret these molecules right here. You might have seen them as one of your drawing options in our homework, okay? It's a whole sort of thing. The ACS loves chair conformations of cyclohexane. So that's like a whole topic where we learn how to draw these things and interpret them, okay? Bottom line is, it's got enough carbons now that it can kink itself and adopt those perfect 109.5 bond angles. Not only that, but if we look at our Newman projection here, we look down these two bonds, we see that everything is perfectly staggered, okay? So why is a cyclohexane so low in energy? You have both ideal bond angles and no torsional strain, right? And again, by that, I mean perfectly staggered bonds. All right, so again, we're going to spend a lot of time talking about this structure right here, this conformation of cyclohexane. We're kind of going to do a deeper dive with that particular structure than we are with these other ones. We're going to save that for next time here. In the remainder of this class, we're going to go back and revisit the topic of nomenclature, but now add in our new functional group, these cyclic alkanes. Okay, so how do we go about naming our cyclic alkanes? All right, so let's start out with our hexagon. Okay. This molecule right here is called cyclohexane. All right, and that is just the generic sort of formula that you will use for naming your rings. They're all going to start with cyclo. You're going to have whatever that prefix is for the number of carbons. And then because we're still talking about alkanes, they'll all have that ending ANE. So in this case, I had a 6-carbon ring. 1, 2, 3, 4, 5, 6. So that's why it was cyclohexane. All right, so then everybody take a second and name the square and the pentagon. that square be called? Cyclobutane. All right, 4 carbons is that prefix bute, so cyclobutane. All right, and lastly, the 5 carbon ring, cyclopentane. All right, cool. So, kind of like with our straight chain alkanes, that's all well and good, right? Easy enough if there's nothing on it. But what do we do if we got crap sticking off of our ring? How do we name those molecules? So we're going to go back to our set of rules. We got those same set of rules, and we're just going to annotate them with these new sort of considerations that we have. So let's take a look. All right. These are going to be mono substituted rings. So by that I mean I'm going to take my ring, and I got this one thing sticking off of it. So, step 1, same as step 1 was before. What's step 1? What is it? Find the parent chain. Yeah, we're going to find and name our parent chain. Okay? And before, we were looking for this longest continuous set of carbons, right? That's how we found our parent chain. For the rings, we're going to go about it a little bit differently. Okay? The ring is always the parent chain. Okay? So when we're talking about cyclic alkanes, we have a very simple rule where the ring is always the parent. It doesn't matter if the ring has less carbons than the substituent. The ring is always the parent in these molecules. Okay? And truthfully, in the awful world of nomenclature, there are some examples where they don't consider it to be that, and we're just going to pretend like those don't exist. All right? So, as far as we're concerned, the ring is always the parent chain in the molecule. All right? What was step 2? The substituents. So we're going to find and name our substituents. All right, and there's nothing different about this step here. Still going to do it the same. So actually, I guess let's do the first step. We got to find our parent chain. It's going to be this 1, 2, 3, 4, 5, 6 membered ring. All right, so my parent chain is the cyclohexane. We're going to find and name our substituent. That's these 2 carbons here. So what would this be? An ethyl group. Okay. What was the third step? The numbering. All right, so now we got to number our parent chain. And this is going to be where we see sort of a big difference between our straight chain alkanes. In our straight chains, we had one of 2 ways to do it. Front to back to front, right? And it was one of those 2. We just had to make a judgment call on which one of those 2. For a ring, there's no logical starting or ending point, okay? So what you do is you always start with carbon 1 at the substituent, right? Wherever that substituent is located, that becomes carbon 1. So we're going to start carbon 1 at our substituent. All right, and the last step was to assemble our name, put everything together. All right, But this is where we're going to see something a little bizarre. Okay? Let's just put two examples side by side here. All right, so we said we're going to start numbering from here. This was an ethyl group. My parent chain was a cyclohexane, so this would be 1 ethyl cyclohexane. But let's say I'm going to pick up that ethyl group and I'm going to move it to a different position on my ring. All right, I'm going to stick it down here instead. Everybody take a second and give me the name of this molecule. What would it be? The same thing, right? Because wherever that substituent is, that's where I'm going to start numbering. This is also 1 ethyl cyclohexane. So because of that, because that substituent is always going to be on carbon 1, we don't bother to write the number in the name. We just say ethyl cyclohexane. There's no such thing as 2 ethyl cyclohexane or 3 ethyl cyclohexane, right? Because no matter where I move it, I'm just going to renumber things so that that's carbon 1, okay? So when we get to our assemble our name for our mono substituted rings, we do not bother putting the locate. All right. So now let's move on to not just one substituent, but now we're going to move on to when we have multiple. So multi-substituted rings. All right, and spoiler alert, now you are going to have to put those locants in, because you got to tell where the two substituents are positioned relative to one another. Okay, so it's only for the mono substituted, when there's only one group on there, that we get to omit it. What we're going to see is when we have multiple ones, we have to include both. We have to include that numbering system. So let's take another example here. We'll do a pentagon. All right, I want you to do these first 2 steps for me. Find the parent, name the parent, find the substituents, name the substituents. So I'm going to find my parent. Always going to be that ring structure. So my parent is a cyclopentane. All right, one substituent is 1 carbon, the other one is 2 carbons. we said that 2 carbons would be an ethyl group. What's it when it's 1 carbon? A methyl group. All right, and here is going to be the pain in the butt when it comes to these rings is the numbering step. Okay, we got to decide on a numbering scheme here. But again, carbon 1 could be either one of these carbons that has a substituent. All right. The other question as I always get asked is, oh, do you number clockwise or counterclockwise? You got to do both. You got to compare both, right? If I take this molecule and flip it over like a pancake, it's the exact same molecule. So we can't just kind of commit in our mind to going one way around. We got to look both. Okay. So what do I mean by that? Let's start. We got a few. That means that we have just more numbering schemes to decide between, basically. Okay. So I'm going to start numbering with my ethyl group as carbon 1. And we're going to look at all our different numbering schemes. So the first thing I'm going to do is go clockwise, right? So that'd be 1, 2, 3, 4, 5. Okay, so this would be 1 and 4. All right, that's where my substituents are. And this step right here, maybe you were able to do it a little bit lazily where you didn't list these numbers previously. There are going to be so many more options that it's going to be really helpful to keep track of what your numbering schemes are giving you here. Okay. So then I'm going to do in purple going the other way. My ethyl group is still 1. 1, 2, 3, 4, 5. So in purple it's 1 and 3. So which one am I going to pick here? Stick with red or purple? Which one's better? Purple. All right. So we're not done yet though. I'm going to just get rid of the red because we decided. I got to repeat the process, but now I'm going to start with my methyl as carbon 1. All right? So again, I can go clockwise. 1, 2, 3, 4, 5. I got a 1 and a 3. If I go counterclockwise, I got a 1 and a 4. So it's not going to be my orange one. All right, so I started at the methyl group. I went clockwise and counterclockwise. I'm comparing those two. My counterclockwise, which I did in orange, gives me 1 and 4. That's definitely not going to be the winner here. All right, so let's just put these other two next to each other. All right, so in my red number or my blue numbering scheme, I'm 1 and 3. In my purple numbering scheme, I'm 1 and 3. So I have a tie. What do I do to break our tie? Alphabetical order. Okay, so because of alphabetical order, that's going to make my purple numbering scheme the correct one. Okay, so bottom line is we're going to have way more options to number our ring because we can start at any one of those carbons, right? And any one that has a substituent on it, and we can go clockwise or counterclockwise. So we're going to have to do a little bit more decision making here. In this case, it's the 1 and the 3, so 1 ethyl, 3 methyl, cyclopentane. All right, so when we're doing our numbering of our parent chain, we're going to start at C1 at the substituent. We can say at all substituents. And we have to number both clockwise and counterclockwise. All right, so we had to update our rules a little bit here. Finding the parent chain. Our now new update here is that the ring is always going to be the parent chain in these molecules. There's nothing new about naming the substituents. But when it comes to numbering, we got to start with carbon 1, add our substituent, and we can go clockwise or counterclockwise. We're going to have to test them all. Okay? And then lastly, for mono-substituted rings, when we assemble the name, if there's only one substituent on there, we don't bother writing the number for it. All right, so now let's just put these into practice for the rest of class here. We're just going to do a bunch of examples. It's like geometry class on steroids over here. right, so let's do this first one. What's my parent chain? In the box with the little squigging on it? The cyclobutane. So the ring is always my parent chain. Right, and so notice that in this example, my substituent, 5 carbons long. My substituent's actually bigger than my parent chain. That's not something we would have seen with alkane nomenclature, but is something that we will see with our cyclic alkane nomenclature because the ring is always the parent. Right, so this is a 5 carbon substituent, so that would be a pentyl group. There's only one substituent on this ring, so I'm not going to bother labeling it as one pentyl. It's just going to be pentyl cyclobutane. All right, my next problem here, my triangle is the parent. So my parent chain here is my cyclo what? Propane. But now I have 2 substituents, a methyl group and a 1, 2, 3, 4 carbon group, which we call butyl. Now I got more than one of these, so I am going to have to include my numbers. Okay? I'm going to start at methyl here as carbon 1. Should I go clockwise or counterclockwise? So you got to do them both, but sort of as you get better at it, you'll be able to see which one's going to give you the smaller number, right? So 1, 2, 3, or 1, 2, 3. You kind of want to always count towards the other substituent, right? Because you're trying to have the smallest numbers in your name. And if I do my butyl group, start there, I'm going to go the other direction. So both of these are tied. I got a 1 and a 2 in my blue and a 1 and a 2 in my red. So since I have a tie, I'm going to revert to alphabetical order. So in this case, my butyl group is going to come first. 1 butyl, 2 methyl, cyclopropane. All right, let's take on this ugly thing next. First of all, 7-sided polygons, the hardest to make look pretty. All right, I even studied a 7-sided protein that was in a ring. We drew these all the time to represent, and this is the best that I can do here. All right, they are very difficult to draw for no good reason. But yes, my parent chain are these 1, 2, 3, 4, 5, 6, 7 carbons. So that would be cycloheptane. Okay. And I would have actually accepted 2 different names here. I didn't specify. You could give me the common name of this molecule or the systematic IUPAC name for this molecule. We got 1, 2, 3, 4 carbons in a T here. What's the common name for that group? Tert butyl. So our little T is tert. So this is tert butyl. There's only one of them, so I don't have to put the number. Right? I can just say tert butyl cyclohexane. If I'm going to do the IUPAC name here, all right, then we're going to look at this substituent. I'm going to number my substituent where I start with 1 at the carbon that's connected to the parent. So now this is a methyl group. This is a methyl group. All right, these were these branched substituents we talked about last time at the end of last week. So in parentheses, 1, 1, dimethyl, ethyl, close my parentheses. All right. Let's do this one here. What's my parent chain here? 1, 2, 3, 4, 5 carbons in a ring. So my parent chain will be a cyclopentane. I get a methyl group here and here. So what's going to appear in my name when I refer to these two methyl groups? Dimethyl. Okay, but we got another one over here. And this one is an ethyl group. All right, so let's put down some numbers. I'm going to start at my ethyl group. My methyl group is closer if I go counterclockwise, right? So 1, 2, 3. Or I can start at my methyl group and go the other way. 1, 2, 3. All right, let's take a vote here. Who thinks we should pick the blue numbering scheme? And who thinks we should pick the red numbering scheme? Who didn't vote? Lazy asses. All right, so we don't have a tie here. You gotta be careful. This is one that's very, very tempting to think that we need to do a tiebreaker. There is no tie here. If I'm listing my numbers in my red numbering scheme, one of those methyl groups is at carbon 1, the other one's at carbon 1, and my ethyl group is at carbon 3. If I look at the blue numbering scheme, my ethyl group is at carbon 1, and my two methyl groups are at carbon 3. So I don't have a tie here. I'm going to go with my red numbering scheme. So just be careful. Very easy mistake to make. If we got two methyl groups, even if they're on the same carbon, we got to include the location of both of them. When I put my name together, I'm still going to put it in alphabetical order. So 3-ethyl, 1,1-dimethyl, cyclopentane. All right, and then last one here. These are also surprisingly hard to draw. Your stop signs, your cyclooctanes. Okay, and just to be clear, cyclooctane has two O's in it back to back. They're two different sounding vowels, the cyclo and the oc. Okay, so both of them appear in the name. All right. I have a methyl group, a propyl group, and an ethyl group in this molecule. All right, the last thing I'm going to have to do to finish it off is to decide on a numbering scheme. If you have not already, I want you to try to figure out what your numbering scheme for this molecule should be. I will give you a hint, there is also not a tie here. There's going to be one that you get to just by that. I want the lowest numbers consideration. All right, so we got like, 6 different options that we could have for our numbering scheme, starting at each substituent, going clockwise or counterclockwise. All right, so let's start with my ethyl group. 1, I'm going to count towards the other one. I can kind of see that I should go counterclockwise, right, because that's where my other substituents are closer. And let's just make a list here. This is 1, 3, and 4. Okay. Let's go to my methyl group. If I start here and go clockwise, 1, 2, 3, 4, 5, 6, 7. So that's a 1, a 2, and a 7. Okay. I'm going to have to, this is going to get ugly. I'm going to use a bunch of different colors. If I go the other direction, 1, 2, 3, 4, 5, 6, 7, 8. That's a 1, a 3, and an 8. So which one can I scrap? Actually, I guess I'm down to just one here, huh? My blue one's worse than the red. My red one's better than the green. Okay, so let's keep the red one. So it already nixed the blue. And if I start at my propyl group, do I want to go clockwise or counterclockwise? Counterclockwise towards the other substituents. 1, 2, 3, 4. So now in orange I have a 1, a 2, and a 4. So which one am I going to go with? The orange one. Okay. When I put my name together, I still got to put it in alphabetical order. So this would be 4 ethyl, 2 methyl, 1 propyl, cyclooctane. All right, again, just rolls off the tongue. Cool. All right.